Yeah, welcome, Dr. Andrew Schloss and
Thank
Dr.
you.
Robert van Rooyen. We are very excited to have you here. You've been to Lethbridge once with your amazing instruments. Remember a concert with you 2 years ago, and Robert showing the instrument in detail. So I was so amazed by that I thought when the opportunity came up, we should, get you back and show us some more. And so I'm very excited to have you. So uh,
Thank you.
welcome. And
Thank you very much.
Thank you, George.
So I'm going to start, and then Robert will take over, and then I'll come back. So I'm Andrew Schloss. I'm professor of music at UVic, and happy to see Jordy was here today. He's one of our students. So thanks so much for inviting us, Georg and Amandine, whoever else was part of that. We were here in 2000, or there, I should say, in 2018. That was the first time we've been to Lethbridge, and we're happy that this is possible. Using Zoom today instead of coming in physically. And so it's going to work fine. The one thing we cannot do today is live demos. And so you can't actually physically experiment with our instruments, which of course would have been nice. Anyway, so Robert did his PhD at UVic and built this amazing instrument called the Mectrum, which is half of our presentation. So let me begin. Wait a minute. There we go. Okay. So I just want to start with an interesting slide that was, this picture was taken in 1992 at Karma when David Jaffe here and I were doing a concert together at Karma. It was actually the 100th anniversary of Stanford University. And what's amazing about this slide is that these sort of founders of an entire field were all together in the same room. You can see Leon Theremin in the center, who was kind of started this whole thing in the early 20th century. But Chowning, who invented FM, Paul Lansky, who is a well-known composer of computer music, Bob Moog, David Wessel from Senmat, Roger Lynn of Lindrum, David Smith of Sequential Circuits, Don Buchla, Ton Overheim of Overheim Synthesizers, Max Matthews, the guy who first made computer music. So it's kind of amazing to see all these people together in one room. And the reason that I wanted to show this slide is not just, my pride that I'm actually in the room with all these people, but to say to everyone, all the younger generation, how incredible it is to be in a field where, now many of these people are gone now, but be in a field where you actually know the founders. I mean, there's really nothing else quite like it. So we're still in this very fertile time when we're inventing a field. It's obviously way, way more developed than it was when I started in the 70s, that's for sure. And nobody had the slightest notion of where it was going back then. It's progressed incredibly fast, and you're all really lucky to be doing this now. And also that there's so much research to do and so much interesting employment possibilities these days. Anyway, okay, so now Robert, as I said, got his PhD recently building the Mectrum, and Robert and I have since started a company called MIST, Music Intelligence and Sound Technology. And we have two instruments that we've made so far, the SDR drum and the Mectrum. So the mission of MIST is sort of not that different from our university mission, really. Research and development of musical instruments, being a resource for musical instrument makers, and the idea that this could advance music education in various ways that we haven't even thought of yet. I have been working on the radio drum since the 80s, since I first met Max Matthews at Bell Labs. I'll get to that later. But anyway, we decided that maybe it would be possible to make more of these instruments and get them out to people. I've had many people over the years ask me, where can I get this thing? And Max Matthews and Tom Overheim made some radio drums and radio batons over the years, but and they did sell a few to universities, but generally speaking, these things were unavailable. Hopefully now that will change. Just want to double check. Can everyone hear me?
yes, fine.
Yes. Great. Okay, good. All right. So inspirations. As I mentioned, Max Matthews, the father of computer music. Now, sorry, I'm getting that unstable internet message again, which worries me, even though I'm now using cellular data. So let's hope I can get through this before we lose the connection. In any case, Max Matthews is considered the father of computer music. He's the guy who first made sounds with a computer in the 50s, and the guy who wrote the first, sorry, just want to set something up here. Okay, the guy who first made music, and the guy who also wrote the first software for computer music, Music 1, Music 2, and so on. That was all written in Fortran. And his music was used in Stanley Kubrick's 2001. Bob Bowie is a robotics engineer at Bell Lab, not as well known as Max Matthews, but he worked with Max and did a lot of amazing work. Max himself was so ahead of his time. He was doing a real-time system in the 60s called the Groove System. He did that with Dick Moore. And then he started doing the radio baton in the 80s, radio drum, radio baton, and there were many different versions of that over the years. So Max is definitely an inspiration. Trimpen is a German artist who's been living in Seattle for about 30 years. He makes acoustic sculptures. He's an amazing artist. There's a movie about him, if you're curious. It's called The Sound of Invention, if you want to know more about Trimpen. And the third inspiration is Henry Brant, who's a composer in the tradition of Charles Ives and Carl Ruggles. And Henry Brant died a few years ago. But one of his areas of expertise was spatial music, using space as a parameter in composition. He wrote only acoustic music, but he was definitely an inspiration. He was also a professor at Bennington, where David Jaffe and I studied. Okay, now getting to the history of this. So the instrument that I play, the radio drum, is a capacitive instrument. So in that sense, it's related to the theremin. Now, Bob Bowie, the robotics engineer, now retired, was doing all kinds of experiments way back in the 80s on touch screens, and he invented all kinds of things that AT&T didn't even know what to do with back then. He invented a clipboard that you could take notes on, and then they would be transferred to your computer. But he was really, really ahead of his time. And so Bell Labs actually didn't make a lot of the things that he invented. But the radio drum was a capacitive sensor. Now, interestingly, it wasn't intended to be a drum. I would say initially it was probably just intended to be some kind of 3D mouse. And they didn't really know what to do with it. So since Max was interested in music, he decided to try it out as a drum. So it's basically a sensor that knows where the sticks are in space. And it's not fully 3D, it's sort of 2.5D. I'll get to that in a minute. Now, the original radio drum was strictly analog, but of course, at some point, the data from the radio drum was digitized, but it was an analog sensing device. And I have been working on this thing since I first met them at Bell Labs back in 1986 or so. Now, you might wonder, why am I still using this technology? And it's interesting because in the high-tech world, something that started in 1986 is absolutely centuries. It's really an old instrument. But there are two things I would say about that. One of them is that it's good to play an old instrument because it means that you have actually experience with it. I think one problem with our field could be that people move on to the next thing too fast. And people don't play the violin for 4 years and then say, oh, let's see, what else can I play? So the time that you use an instrument is valuable over, thousands of hours. So anyway, that's one thing. Another thing is that if you're trying to sense just location in space, a very basic idea, that overlaps with all kinds of things, especially game controllers. And there's much, much more money and more users in game controllers. So lots of people from the Max MSP and NIME community over the years, NIME meaning New Interfaces for Musical Expression, they have, the world of game controllers has contributed to music because we've borrowed the technology, starting with the Wii, or even before that, the Mattel Power Glove, way back, the Kinect, the Leap. They were amazing and lots of money went into the research on these instruments or these devices, but they tended not to be fast enough, even though they were used for sort of virtual tennis and other games. The delay is still not so great, there are just various limitations of all these things. So the capacitive sensing is still useful. It's a very simple technology. It has extreme accuracy in space near when the capacitive surfaces are near each other. As you move away, the error gets a lot worse. So that's a problem that we still have. They have arbitrarily low latency in the sense that it's just an analog signal, so you just digitize it at whatever speed you want. It's different from video tracking like the Kinect, where you can't get better latency unless you have a faster camera, because it's going to be half, the Nyquist is half of the sampling rate, and the sampling rate is basically the frame rate like in a movie. So if you're a percussionist, as I am, you want something that's super fast and super accurate right near the surface so that you can track very tiny motions. And of course, if it's a 3D instrument, you can also do all kinds of other things. But anyway, as I said earlier, the bad thing about this is that as you lift your stick up from the surface, the error gets much worse. So now, I mentioned that this was created at Bell Labs, and it was sort of a solution in search of a problem in a way at first. They didn't know what to do with it. I was teaching at Brown University in Rhode Island, which is not that far from Bell Labs. And so I decided to go down and see it. And I met with Max and Bowie, and I saw their instrument, very crude. It was at that time, it was a serial instrument using RS-232, which is an old serial protocol running at 9600 baud. And they showed it to me. They showed that you could track the position of the sticks, but they didn't really know what else you could do with it, and that's why they wanted me to have one. So they loaned me serial number 3, which I still have. It was a sort of a permanent loan. And then over the years, I got to know them better. When I first met Max Matthews, I was pretty intimidated by him because he was the guy, and then he was the founder of the field. But I got to know him much better, and over the decades following, we became really good friends. And we were always kind of in a dialogue with the instrument, how we could make it better. And Max really thought of it more as a conducting device than as a drum. But since I'm a percussionist, I kept pushing pushing the boundaries of how it worked as a drum, how sensitive it was, and so on and so forth. Max was using it to conduct music. And in that way, one of the many, many things Max did way ahead of his time was he basically invented Guitar Hero, or whatever you call that thing where you play a sort of fake guitar and it triggers music from memory. And that is an idea that Max came up with way before anyone else. But Guitar Hero and all the other things like that can be thought of as deriving from his idea. He called it the sequential drum, where you put the music in the memory of the machine and then you tap it out. And you can tap it out in different ways. Like if it's in a 4/4, you can tap the tempo and then it'll play the music in between the taps. And that gives you more bandwidth as a performer to control other things. So anyway, for me, what I did was I looked at this code, which was just like 2 pages of C code. And I saw things that I didn't see any use for. For example, looking back on it, I remember that since the sticks were transmitting at different frequencies, you could tell which stick was which hand was which. And I thought, well, why would you want to know that? I mean, the drum doesn't know that. Of course, I very quickly learned that that was really valuable and powerful information to have. Anyway, you can whack this thing like a drum. Impact doesn't matter, but it knows where the stick is. So you can figure out when you hit the drum, so to speak. And then you can make any possible sound, which can be electronic or physical if you're using robotics. And so that's what we call whack mode. Continuous mode is the smooth parameter change with 6 degrees of freedom, because that's X, Y, and Z for the 2 hands. So that's 6 degrees of freedom. And that's a smooth parameter you can use to control anything you want. And then there's something I invented that I call magic wand mode, which is where you re-trigger at a given rate in space And that allows you to play really virtuosic, complicated rhythms, which I'll show you in some of the videos. And then there's another mode that's kind of interesting, that's sort of a haptic thing, which is really for the user's benefit. The computer doesn't really care, and that is if you have foam on the surface of the drum, when you push the stick into the foam, it kind of gives you a new domain that can have different responses from the other ones. So this is Max and me and David Jaffe at Seamus in Eugene back in 2006. Seamus stands for Society for Electroacoustic Music in the US. It was started by John Appleton. And we were using one version of the radio drum. I don't think you can see my cursor here. This is an antenna here. It looks like a backgammon board, and it's covered with plexiglass to keep it from being damaged. And there's a DB15 cable here going to the computer. And then there's a rubber pad on it. I searched for the right kind of rubber to play on, because that makes a big difference for a percussionist. Okay, so here's the new version of the drum. Basically, the drum was 100% analog in the old days, and then it was digitized somewhere, of course, to work with your laptop. In the very early cases, it had just serial data, and then it was USB and other, or MIDI, actually. MIDI version lasted a long time. Max and Oberheim built those. But we finally decided that we really needed to build a new one, because we kind of reached the end of the road. What happened was Bob Bowie designed and built a drum just for me, a custom drum, which was fantastic that he did that. And I used that for a while. The problem was I had the only one. And I remember one time, I'm going to show you a video of this. I was invited to perform at the Other Minds Festival in San Francisco, and on my contract it said I had to have a backup. I had to have more than one instrument. And so I said, oh yeah, sure, no problem. Because we were building a copy, of course, and Bowie gave us the schematics. The problem was that Bowie was an analog genius, and we found that his tweaking of the analog circuits was impossible for us to duplicate. So we made copies of the drum using his circuit diagrams, but they never worked properly. So I was really worried about having only one instrument in case something went wrong. Anyway, Peter Dries, an electrical engineering professor at UVic, thought we could probably use software-defined radio, which is a well-known technology for radio, where you basically digitize from DC to daylight, as they say, and then you use the computer to analyze the radio signals. So we're doing the same idea here, but much simpler. We have each stick transmitting at like 100 and something kilohertz, 2 different frequencies. Then we have the antenna, which is this, picking it up, and then we digitize it. And basically, this is a daughter board on an FPGA, a field programmable gate array. And this was designed by our student, Daryl Ring. And this is very inexpensive. You can buy an FPGA, and then you can make these cards. And basically, using SDR technology, software-defined radio drum, we duplicated the functionality for much less money, and it was much easier to duplicate. So Robert stepped in and built this enclosure, and we made 5 new instruments. So we are on the way now. Here's what the new instrument looks like. This is foam on top, and that really, like I say, if you're a percussionist, the physics of the foam make a lot of difference, even though they make no difference to the sensing itself. So I'm going to start with a video of a piece that I did actually at Lethbridge at IAST in 2018, and then I did it again a few times. This is a performance I did in Brazil. Now, this is sort of a demo as well as a performance for this talk, because it shows a few things that you can do with the pairing of the radio drum with the mech drum. So what this is going to show is how you can track the position of the sticks in real time, and then you can send that over Ethernet to the mech drum. And unlike any other robotic percussion, and we'll talk about this later, this is not waiting for a note on. It is tracking the position of my sticks, as you'll see. So the drumsticks will follow what I'm doing with my sticks. So the sensing is happening with the SCR drum on the left side as you're facing it. And then there you can see the mech drum moving. So that's getting position data from my sticks. This gives you the chance to do two things. One of them is reduce latency drastically, which I'll talk about a little bit later. And the other is to have a fabulously huge dynamic range, which is so vast you can barely hear it. And that's something unusual with robotics. Most robotic instruments don't have such a dynamic range. So now you can hear it very quiet. Now I'm squishing into the foam here, and that's that other haptic dimension I was talking about. Now I'm just playing normally, and it's just following everything that I do. And this is the same piece that I did at Lethbridge. Now, in the interest of, I just had a timer over here, in the interest of making sure we have time, I'm going to skip ahead in a second. You can see it's tracking me pretty well. There's a bit of a delay, but it's pretty good. So here's a one-to-one correspondence with my commands. Now you might say, and you know, if you're a percussionist, you might say, well, so what? I can play that. I realize that. We're very aware of not just doing what humans can do. Why would we bother? You know, let's just have humans do it. But we also can move into other dimensions that are not physically possible humans. So that was a one-to-one correspondence, but I can also have mappings from my sticks to algorithms that are written in MaxMSP, where the drum is sort of somewhat autonomous, but it's still following my lead. So let me show you what that looks like. Somewhere around here. So you can see here, it's playing this super fast, buzzy sound. So I'm not playing every stroke, I'm triggering the strokes. And then I have written software that maps different things like the speed of the stroke, where it is, the density, which hand is playing, and so on. So let's see what that looks like. I'm not playing every stroke here. It might look like it. Now you can see that I'm not. So I just have algorithms that I'm controlling from my instrument. Could be controlled from the keyboard, but the modality would be totally different. See that it's way faster than human, and it takes you into a new space musically. In the interest of just not running out of time, I'm going to keep moving here. So, and then after Robert speaks, I will show you some more videos of performances. So let's move to the mech drum side. First, I'll talk a little bit about robotics and how I got interested in them. The first thing you could say is, well, you know, there's a tremendously interesting history of science fiction and the golem and the sort of you know, fantasy of robots. And there's also mechanical instruments going back centuries, so it's not a new idea. And then there's sort of the anthropomorphic robots. It's kind of more like, especially in Japan, they have the, you know, the robotic puppies and stuff like that. That's kind of an interesting area. And then there's, in cinema, they had mechanical orchestras that are related to mechanical instruments. And then there are autonomous performers. Where you could have sort of a cyber musician or someone who plays along with you in some way. And then there's the idea of telepresence where and this is kind of what I'm doing with the mech drum, for example, where I make a motion in space and then somewhere else in the world, usually in the same room, but not necessarily, it plays an acoustic sound, the drum plays. One sort of sick joke is that one could use this now with the pandemic. You know, I could put the drum in a concert hall and I could play somewhere else where I was safe from the virus. That's the telepresence idea, which I used to make that joke with, you know, radioactive concert halls, but now it would be viral concert halls. Okay, so another motivation for me artistically for the robotics is that the antiphonal aspect of music is something that hasn't been explored that much. And Henry Brandt did this, Charles Ives did this, when you spread the musicians out in space. And if you do that, timing becomes challenging. So my sort of metaphor for the percussionist is having 20 or 100-foot arms where I can reach across the concert hall and play an instrument on the other side of the room. And this is really fits into the sort of whole paradigm of multiple instruments that percussionists often play, where they have a stage full of instruments and they're running around trying to play them all. And now I can reach across and play an instrument on the other side of the concert hall. So that allows me to do really interesting spatial things. There's also another aspect of electronic music that we have gotten past in some ways, and that is, the frustration with loudspeakers. Morton Feldman, the famous composer, used to say, loudspeakers are like tombstones. He found them too inert, and in one physical sense, they don't have the complex directionality of real instruments. So we love the idea that the sound comes out of the instrument as it would, and it's a real acoustics instrument. So in other words, I could do a concert with computers and electronics, but all the sound would be acoustic. The other thing is that sound generation itself is visible to the audience. They can often, not always, they can see the instrument being struck somehow, instead of the invisibility of laptop music where you really can't tell what's going on or how the sound is being generated. So the physicality is important. So, there's the music box, the player piano, and then there's the Yamaha Disklavier. These are all mechanical versions of pianos. Trimpin built a Vorsetzer, which I'll show you later, in order to play Nankara's music. Anyway, we believe that cause and effect is important from the point of view of performance. It doesn't change what the music sounds like necessarily, but it changes the experience of the audience. And I wrote a few articles about this. One of them is called Intelligent Musical Instruments, the Future of Music Performance or the Demise of the Performer. And another later article called Using Contemporary Technology in Live Performance, the Dilemma of the Performer. And this is about really the problem that the audience is lost. They have no idea what you're doing on stage. And of course, since the beginning of time, we have had obvious cause and effect with all musical instruments by definition. So when you bring a computer into it, you lose that. And it sounds sort of old-fashioned to want to bring back cause and effect, but I feel that it's really critical for the audience to follow what's going on. So it's something that I pay a lot of attention to. So we have various strategy. MIR has become more and more important to allow the instrument itself also to make decisions based on MIR techniques. We have the idea of telepresence where I move and then the automaton plays something because of my motion or whatever, what I send over the wires. It can also be an automaton where it's making its own decisions. And then using space as a parameter, I already mentioned that, where the instruments can be synchronized precisely even though they're far apart, because we know that sound takes 1 millisecond per foot to travel. So if an instrument is 30 feet from you, it takes 30 milliseconds for the sound to get to you. So that just can make life very difficult if you have instruments spread out. But if you have robotics, you can fix that problem. We don't try to mimic humans because we feel like, why would we do that? We might as well have humans do what they're good at, and computers and machines do what they're good at. So now we do use mappings a lot where, the gesture of the musician can be expanded drastically into data for the robot. So it's not a one-to-one mapping necessarily, it depends. And where the intelligence resides doesn't matter. It can be in the machine, it can be in the laptop, it can also be in the musician's brain. That's not so important. Now, here's a big problem with robotics that we're dealing with. The big problem is very simple to describe. The problem is that if you're using, say, a solenoid, and if you're using MIDI, those two worlds work well together, except for one big problem. If I go like this, and I move my wrist or a stick, and you send a note on, it's like pressing middle C on the piano. What happens in a real piano is that the key moves slowly down, and then it hits the string. And the musician, the pianist, is aware of that, either consciously or pretty much mostly unconsciously. And if the pianist is playing accents, the louder notes, it pushes the key much faster. The problem with robotics and MIDI, that concept of a note on, is that if you wait till the note on is sent, which is to be at the bottom of your press on the keyboard, for example, then you send the note on, then the robot starts to move, or the solenoid. You're already late, because even though you're sending the note on very accurately, that's when the robot starts to move. So it's going to be very late. There's going to be large latency, but worse than that, the latency is going to be dynamic dependent. In other words, the quieter the note, the slower the response, because it's moving slower. And how do musicians deal with this? Well, they deal with it based on 2 million years of evolution. The squirrel knows how fast they have to run across the street, and if the car speeds up, they do a bunch of calculations. Even the squirrel can do that. The pianists, when they're playing fast, the finger moves quickly, and when they're playing slowly, they anticipate drastically so that they arrive at the bottom of the hit of the stroke with their finger, and they fix that problem of variable latency. So that's a huge problem. Now the Mectrum, we're going to switch over to Robert in a second, solves that problem because we can, if we want to, we can send position data so that the stick is moving with my stick. So it actually knows that it's coming towards the surface. So it can be quote unquote psychic. It doesn't have to wait till a note on before it starts moving. So now we're going to switch to Robert, and he's going to talk about how he designed and built the Mectrum, and then we'll show you some performance videos. Okay, Robert, take it away.
Thank you, Andy. Can you hear my audio okay?
Yeah.
Okay, terrific. I was having some issues with my headphone. Okay, so yeah, the Mectrum is the result of my research in the human motion, and I sort of listed a few objectives here in the development of this instrument, which is really to accurately reproduce human motion and the velocities, acceleration, and position where the strikes occur, which are quite challenging electromechanically. The other part is this low latency, right, that Andy was talking about. The latency right now is on the order of 20 milliseconds, which is just barely perceptible. And that was key to being able to do live performances with the instrument. The instrument is also self-calibrating. So you can, it sits on a tripod normally, and you would put it behind a drum. And there is a user interface where you would select calibration, and it would then begin to automatically discover the surface of the drum so that it can know where the strikes can occur sort of in 3 dimensions. It has a modular striking implement system. So right now we're working mostly with traditional drumsticks, but you could also go to mallets or perhaps brushes, these type of things. The evaluation has determined that the dynamic range is equivalent to human performance and actually a bit beyond. It does consist of a fairly robust design. You can imagine there's a lot of forces taking place with all the sort of banging on the drums, a lot of vibration into the instrument. So it's very sturdy. It was designed to be that way to tolerate that type of abuse. And sort of lastly here is to create a generalized research platform for further study in some of the aspects of AI and other things. Let's try next slide. Okay, so the features here, just a quick list. There's a control panel to do calibration, configuration, and look at some of the status. It consists of 4 motors, which I'll show a little drawing of. But these motors allow 4 degrees of freedom, basically 2 for the left and 2 for the right stick. And there's quite a bit of other features in terms of monitoring internal temperature and current and voltage and all these things to make sure the system is working properly. It also has an internal fan, which actually never comes on. It doesn't get hot enough, but it can control its own temperature if it needs to. It has a MIDI interface, USB interface, but primarily the 3D motion data is transferred as OSC messages. I mentioned the robustness of the case. It's a CNC aluminum enclosure, and it has some sort of Lexan covers in the front and back So you can kind of see what's going on, and we talked about the tripod already. So we'll go next slide. Okay, here we see a graphic of, on the left, the mechanical situation going on here. So the y-axis motion shown in red, the larger motor is what's driving that through a pivot point, and then transfers through a shaft, and then it goes to the stick itself. And so you can see that motion. And then the smaller motor just behind it is the x-axis motion with the arrows in blue. And to the right, we can see how this is achieved sort of electromechanically, and as well as software in this case, to form a closed loop. So on both motors, at both shafts, we have an optical encoder that allows the system to determine the exact position at any given time. So this is fed through it's called a quad-stir decoder, and then a PID controller. And so this controller determines the rate at which the motors move and where their set point should be. So this is proportional, integral, and derivative control. Out of that comes basically a direction and a pulse width modulated signal that's driving an H-bridge driver chip for each motor. And this is what's varying basically the current and direction of the current into the voice coil actuators. And these actuators work on the Lorentz principle, where basically their motion is proportional to the current, basically the amount of current, and then of course the direction of the current. And we can see that ties right back into the axis of motion to complete the loop. Okay, let's go to the next one. And here we see just a graphic of the electronics. So we have the 4 motors. Each are driven by these H-bridge drivers on a dedicated carrier board, which also has a MIDI interface, the power supplies, and various other support circuits. Plugged into that is the LCD display and user interface buttons. And then driving all of this is a MicroZ 7020 board. So this is a Xilinx FPGA board. So not only is it a large logical fabric for all of the PID control software, it's all running in real time in hardware, but there are also 2 ARM cores, so CPUs, one running Linux and one running bare metal firmware. And it's all being clocked at 100 megahertz in the fabric. And all of this is necessary to get that latency down that we talked about. You need a lot of computing power and dedicated hardware to achieve the kind of speeds that this system is capable of doing. Okay, next slide. Okay, so this next piece, it will be a couple of demos. The first one is one that where I participated in a competition or the Gutham competition at Georgia Tech. So it shows a little bit of sort of the first piece. I'll talk a little bit through it as it goes. And then the next one is a pretty fun experiment we did with Roger Dannenberg from Carnegie Mellon, where we paired it with bagpipes. So let's try that out. Okay, so I'll talk a little bit about that before the setup on the next piece here. So this one is demonstrating a real video recorded performance that was then digitized and a little bit of signal processing to reproduce on the hardware. And so you could see all the 3D motion and the subtleties of the real performance. Now in this case, what we're showing here is controlled by a keyboard. And this isn't a particular musical piece, but more a demonstration that the MIDI keyboard can control the Mectrum, not only just strikes, but as well as all of the rudiments at various speeds, at various elevations for dynamics and so forth. So this is an interesting way to perhaps explore other performance capabilities of the instrument. Okay, we can go to the next one. Okay, next slide. Okay, so this is, yeah, this is the bagpipe thing. So just let it play, and then I'll mention a couple of things afterwards. Go ahead. So that's kind of fun. We like where it kind of dies off there at the end. So that's Roger there, who had very quickly, I think in the span of what, a half hour or so, modified his code to drive the mech drum in parallel with the bagpipes. And it was pretty aggressive on the data stream coming in the mech drum. It was really pummeling it pretty good. So it's had a good test there. Okay, next slide. So talk a little bit about the design process here and the timeline. So it spanned about 5 years or so, and like most research projects, you definitely start with a deep literature review. What has been done in the area of certainly robotic drumming, but in general with music robotics and motors and all these things. I've discovered quite a few things during that literature review. Then moved on to develop a motion capture system. And actually we can see Andy there at the drum, where I'm recording with a GoPro camera the video and then doing a whole lot of post-processing on it to pull out information in terms of timing and strikes. And separate from this was the development of this analysis software, which is kind of the upper right corner there. And this idea of creating this vector of parameters to drive rudiments. So around 2014, we see first actuator prototype, and that's kind of the top middle where you see the voice coil actuator and kind of this aluminum chassis. And it was initially, there was only 1 degree of freedom, just up and down. And could I actually move this thing? Could it move fast enough? A lot of experimentation there. 2015 was the bulk of the design process, but that's multidiscipline, right? So that's mechanical, electronic, and software, all stemming from these experimental prototypes to understand where the challenges were. 2016, a lot more firmware, sort of a big mountain of firmware, or iceberg as it were, within the mech drum. And a lot of machining, very high quality CNC machining done at UVic to get the pieces. It's well over 450 parts, I think, just the mechanics alone. 2017, a lot of unit system testing, more refinement of firmware, and some integration, right, with the SDR drum. That's when Andy and I really started to tie these things together and transmit data and see if we could control this thing. And 2018 sort of wound up with actually going out to NIME conferences. There was definitely NIME conferences along the way with presentations, but we actually had something to show, right, in 2018. And so we did quite a few performances, and the Sonic Pair #2 is a great example of that. Okay. So a bit of sort of tips along the way and what I've been doing with the mech drum, but just farther back in many projects that I've worked on, is to definitely do literature reviews, right? And this is continuous from the beginning of your research all the way through to the end. Things are always changing. There's always sources of new information in areas you might not even think of. Like I found a lot of work with voice coil actuators in the medical field, which added, more insight on what I could do with the devices. You should develop a clear and concise definition for the design as you refine and learn more about the medium and physical constraints, right? As we go, especially with physical implementations, we learn a lot of things about what they can and can't do, and this could definitely change your direction. You might discover new interesting things you didn't think of before. So you should be open and willing to change your perspective as you move along. A lot of data acquisition analysis is involved. We saw that with the earlier presentations with mixing and so forth. A lot of data is acquired, and then analysis is done on that data to figure out where the meaningful information is. And then prototyping, right? This doesn't necessarily have to be like a robot in this case, but it could apply to software or anything, right? Prototype early and often. Do a lot of physical modeling, simulation. All of these things will help refine and remove the risk of what you're trying to do. Okay. There's a lot of technology out there, right, that can accelerate research and development. So you try to leverage as much as possible and concentrate on the area where you're moving things forward, right? So try to leverage. Try to identify risk, mitigation strategies early on, develop a lot of experiments, collect data, refine that design, and get feedback, from colleagues, friends. This is really, really helpful in getting these perspectives to keep you in the right direction. When you get stuck, or if you're not sure about something, try to reach out to experts, whether it be in the academic world or professional consultants or anything like that, where, a few minutes of their time could be invaluable to keep you on the right track and not get bogged down right in details that you don't necessarily have domain experience in. Okay. Seeking out communities. So I mentioned NIAM is a large community for getting feedback and showing your work and having interesting conversations. You should try to keep the design is interactive and prioritize usability and robustness. So as I mentioned, with this particular instrument, robustness is very important. It wouldn't last too long if it wasn't, so very important there. And if you have people interacting with whatever you're developing, think about that usability. How are the ways that they'll interact with it? How will they use it? How could they possibly break it, right? All of these things. Keep documented notes associated with the design. This is all super important, especially if you're developing papers later on or just trying to remember what you did, right? If you covered a lot of ground. You should always archive your work, especially version control, so you can go back if you happen to break something along the way. And don't forget to develop content. That was something challenging for me. I was doing engineering work right up to the beginning of that government presentation. So I didn't have any time to generate some real content that I would have liked to do. So that's important. Okay. So I'll turn it back over to you, Andy.
Okay, I'm unmuted. So we don't have too much time left, so I'm going to move quickly. I have a lot of examples of actual musical performances. I think I'll only be able to show a small number of those, so I will put them online or something so people can see them. A lot of this research was done at Banff, actually, which is there in Alberta. It's an amazing place. I love Banff. And while I was at Banff, somebody from Italy came and interviewed me and wrote this article in Italian, which is sort of like an electronic musician or keyboard. So this was a long time ago. This was in the early 90s. It was something that people were interested in. Then when I met Trimpen, this amazing sculptor who builds kinetic sculptures. This is at the Experience Music Project in Seattle. It has like 150 guitars that are, and this gigantic sculpture about 100 feet high, all played automatically. And he makes all kinds of sculptures, musical sculptures. So my first example that I'll play you, at least part of, is a piece called The Space Between Us, which was premiered at the Other Minds Festival. This is Trimpen hanging chimes from the ceiling of the concert hall. These have solenoids in them, so I could perform them from my instrument. And this is called The Space Between Us, and this is quickly to tell you what's going on here. There are 2 string quartets spread out through the hall, and there are chimes hanging from the ceiling above the audience, and 2 robotic xylophones and glockenspiel and a disc liver piano. So this piece is entirely acoustic. So it has 8 string players and me playing all these different instruments from the radio drum. It's very obvious that there's complicated mappings going on, because when I hit this drum pad with 1 stick, or even not even hit the pad, all kinds of sounds are happening. This is an entirely acoustic performance. So here's some excerpts of the space between us. The chimes are over the audience's head, like that. And the position of the stick on the surface maps to the position of the chimes over the audience's head. I'm going to keep going because there's many musical examples. This is at EarCom, where I first met Miller Puckett and learned about a program called the Patcher, which became Max MSP. So that really took off for me in terms of what I was able to do with the radio drum. Instead of writing code in C, I could write it in Max. This became later on a trio with Irene Mitra on violin and Ilaria Duran on piano. I became very interested in working in Latin jazz using this instrument. This is a performance with Chucho Valdez, who's a super famous Cuban pianist, one of the top jazz pianists in the world. Trying to keep up with him. This is a piece that he wrote. Not mixed very well, you can't hear the percussion very well. Keep going because we're running out of time. This was at Stanford years later, a much more refined setup that I had with Jovino Santos Neto, who's a Brazilian pianist and composer. this is a trio with Ilario, the Cuban percussionist, playing a piece by David Jaffe that he wrote for the trio. This has all kinds of interesting technology in it that I can't explain now, I don't have time, but I'll show a little bit of this trio performance. Now here I'm just triggering samples. This is all electronic. Here I'm using the 3D aspect of the graph to do signal processing on the samples. So in other words, triggering them with the whack and then modifying them in continuous data. Here I'm getting the notes from the piano via MIDI and changing the timbre of what the pianist is playing. And the arrangement, the order also. And here, this is totally different. I just have, well, this is sort of funny. This is 8 turntables with 8 records, LPs. And I got 8 copies of Jane Fonda's exercise video, and they're being controlled from the radio drum, all 8 turntables that Trimpin made. There are the turntables. This is another, I'm just trying to show you the different modalities. So here we have, again, the radio drum, but now we're controlling Trimpin's sculptures. And Kathy Lewis is a soprano who's singing along with my controlling the various sculptures. I'll just play a little bit of this. It starts out very quiet. Sculptures are made from recycled pianos. Sorry to cut everything short, but I will put pointers so you can hear them. This was done at UVic with a PhD student, Ajay Kapoor, who now teaches at Cal Arts. Here you can see I'm triggering samples of wood blocks, but then I'm also triggering these drums at the same time. So this is a mixture of sampled sounds and real sounds. There are microphones on the drums, and I can do DSP on those. This is using what I call magic wand mode, where I'm triggering at a certain speed, but I'm not actually hitting the drum at all. looks like I'm hitting it, but I'm not. I'm scanning through space. Skip ahead just a little bit and you'll see me triggering the drums and then using signal processing on the sound of the drums. The speed of triggering is controlled by the right hand. So every time I hit with the right hand, the speed changes. Now, super fast and then slow, but fast, but not as fast. Super fast. Now I'm going to go into the DSP part. So you can see I'm triggering the sounds, but I'm also modifying using the 3D aspect, like that. Okay, moving on. This is a duo with Joanna Hood, who's a violist in the Lafayette String Quartet, using more robotics and signal processing. So these are frame drums which have solenoids on them. Again, it can always be a one-to-one correspondence, or it can be one-to-many correspondence, depending on the map. So all written maps. I'm going to move on because I don't want to go too long. I know I'm a little bit over already. This was in Cuba with Randall Jones, and Randy Jones is the founder and CEO of Madrona Labs, author of Alto and Kaibo, and creator of the, what's it called? His 3D controller, his pressure sensitive controller. I'll just repeat Madrona Labs if you want to know what he does. The sound plane, sorry, the sound plane. So this is interesting because it predates Jitter. This is software that Randy wrote. We're triggering both images and sound. Skip ahead a little bit. So here we're triggering both images and sound at the same time. But Jitter did not exist yet when we did this. So it was really difficult to do this kind of work. Okay. Very quickly, this is Trimpen's Vorsetzer. This was created because Carmen Nancaro, the composer in Mexico City, had a bunch of player pianos that were falling apart. So Trimpen built this thing with 88 solenoids to be able to play Nancaro's music. You can see that that whole idea is something that you could not do with a real pianist. Like 16 trills at the same time are not physically possible for a human being. So we're very conscious of going beyond human abilities. And this was the first time we put these two instruments together. This was at 9 in at Virginia Tech, and then later in Lethbridge. And finally, oh yeah, this I guess I just don't have time to play this. This is just play the first 30 seconds of this. This is a whole other world of time-based art. So this was a sculpture that is in False Creek, and I wrote some software that collected the data of tides, which move very, very slowly, and we sped it up by a factor of 2 million and turned it into sound. So I'll just wait till it shows the picture of the sculpture, which is floating in False Creek, going up and down according to the tides, very slowly. There's the sculpture. So my data, you have to collect quite a bit of data before you can even start playing, since it's about 2 million times faster than the tides. Then we created this work to go with the sculpture. There's other things in here, but I think I should skip it because we're over time. So these are where we got our research support from, to the same places that you're familiar with, the people we worked with. And finally, Do we have time for questions? I don't know, but anyway, thank you very much. The applause is deafening. Thank you for letting us speak, and I'm sorry we went over. And I'll let Amandine decide if we have time for questions.
Hey, thank you very much, Robert and Andy. That was great. I think we should take a few questions. I mean, at least for, I don't know, 5 or 6 minutes, and let's see.
Okay. Sure.
Yeah, because we don't have the pizza, unfortunately. So
Okay.
I'm sure everybody can heat up some food at home and go back to the screen in like, 40 minutes or something. So any questions, students, please be active. I see that you get some uploads on the chat, but could you guys share some comments or what you liked about it, please?
Or what you didn't like.
Yeah, well, if you want, but they're usually positive here.
Yeah, that's good. Yeah.
Don't be shy.
And while we're waiting, I'll just say I will post the link so you can watch those if you want, the performances.
Yeah, I was going to ask you if you could share also the papers.
Sure.
Because I can put all of that on their Moodle, and also send it through the DA listserv, because I can see that there's a lot of students who are not in the class, which is great.
Sure.
And also I was trying to find the video link of the documentary of Trimpin.
Ah, yes. I will post that. I know that there's a trailer for the movie. Whether or not you can watch it online is not clear to me, because when they first made that video, it was available only on DVD. But we're in a different world now, so I have to check to see what the access to that video is. Yeah.
I mean, no big urgence, but I'm sure that would be interesting for a lot of our students, and I can order it through the library.
You definitely should. It's a fantastic documentary. Yeah.
For sure. No, it sounds good, and it's the good time in
to watch
confined life to do that.
That's right.
Other students told me that was a good time to play video games, but I think watching video can be also fine.
Definitely.
But yeah, please participate, guys. And I know some of you have done some work, like Carter, if you're still around, maybe you have some questions because you did a project about drum digital music instruments last year.
Well, I'll just jump in. It's Leo Brooks speaking. I'm a percussionist too, and I just found this absolutely fascinating. I'm so grateful that you shared what you did. I'm also disappointed that we couldn't have met in person at the university.
Yeah, because then you could also try it out, which is of course,
Yeah, but thank you so much. Yeah. I have questions, but I'm just processing the whole thing a little bit. So
let me email you. Sure, you can email us anytime. Let me also say that for the first time, I used to do concerts for the last 30 years, and people would say, wow, where do I get one of those things? And the answer is nowhere, really. Now, at least the SCR drum, we have made 5, and we will make more. The mech drum, we could also make more, but it's more expensive. But in any case, this stuff theoretically is available. In the old days, it just wasn't. So that's good.
Yeah, it's an amazing thing about the world that we live in, that we can have CNC machines and 3D printers and all these things that allow us to just make this so much easier, right? So
yeah. The mech drum is still, definitely a challenge to build, but yes, absolutely, yeah. And the thing is, even the expensive mech drum is still I think, in range of some schools, some universities. It's an investment. The SDR drum, because it has no moving parts, could be made in volume for, obviously much less. We haven't gotten to that point yet, but we have made 5 of them. So, yeah. Thanks for commenting.
Well, I will have a question. It's going back to one of the first videos that you showed when I think there was a NIM concert when you were playing on the mech drums. Oh no, that was actually a tablet, sorry, and that sounded like piano. It was like a solo piece. I was wondering, what was your concept in terms of gestures for it? Because I could tell that you were like sometimes triggering a bunch of gestures with just one like trigger. Yeah. And sometimes you were actually playing almost the same amount of notes that we could hear.
Yeah, well, good question. I mean, all of these, every time I play the instrument, since it's a it doesn't, all it does is send data. So the question is, what happens to the data between me and the final result, which is either a synthesizer or in some cases some kind of robotics. And so the answer to the question in general is that the mapping is completely arbitrary. So the mapping can be one-to-one, where let's say one drumstick hit in one location plays one note on a piano, let's say, or it can play chords, or it can play huge sequences of thousands of notes for each hit. So that is completely open, and it's up to the composer. In this case, the composer, if the composer is also a programmer in Max MSP, let's say, then the score is sort of the score of the music actually is the max patch in some sense. Although that's, I have to say, that's combined with the improvisational skill of the performer, because typically we do not store sequences, we store mappings. And the way that we move from one mapping to the next is with the foot pedal, which you couldn't see. So, but yeah, so for example, playing a piano, that was a Yamaha disc luthier. The very first video I played with the two string quartets, I was playing the Yamaha disc luthier and also the chimes and the Glock and the xylophone. But in any case, so yeah, that people always ask me, can you play the same thing twice, and all this stuff. And so no, I can't. Well, it depends on the mapping, but generally speaking, if there's sort of a palette, that's the word we use, it might have a palette of a certain kind of modal mapping, or it might have certain selection of chords or other sort of polyphonic things that are triggered by me, and the position in space or the position on the surface to controls what I'm actually getting out of it. But it can be arbitrarily complex. So one drum stroke, for example, I might have something where the left hand starts a process which would actually go on forever, and the right hand stops the process. And by doing that, I can have very complicated patterns that start and stop very fast, and it's almost impossible to tell. You have to really practice for a while to get used to it. People also ask me, how do I know where I am on the surface? The answer, again, is that these are totally arbitrary mappings. So, for example, the x-axis could be a chromatic scale from left to right, or it could be the surface can be broken up into rectangles, or any arbitrary mapping that you want. And so if you do create a mapping with, say, 12 little rectangles on the surface, then because it's not permanently like that, you simply have to learn it. You have to get used to it, and then you can play pretty much exactly what you want. Sometimes, let's say, if I want to play something more like the Brazilian jazz, then I'll have a mapping where the surface is broken up into little rectangles, and each rectangle is a different drum sample, for example. But yeah, playing the piano is really funny, because you say, well, how can you play the piano with a drumstick? I mean, the answer is simple: software. So once you give the palette to the player, this goes back to what Robert was saying, you have to use it. You have to work with it, because the mapping at first might not make any sense, and then you modify it and you refine it, and then finally get to the point where you're ready to perform with it. And a typical problem that people in music technology have, we all have, I think, is that we spend too much time on the technology, and then at the last minute we work on the music. And I think a really important goal is to finish the technology by a certain date and give the whole rest of the time to yourself to play music. But I think that often gets stretched so that you spend more time on technology and not enough time on music. At least that happens to me. And that's partly because I'm an improviser. If you're doing pieces more like Earcomp's paradigm, where the music is more formal, then that problem is not as severe, because you have a date where you have to give the musicians the parts, for example. That's a fixed deadline. In my case, what I often do, though, is I work with David. And so, for example, in that piece with the 8 string players, 2 string quartets, those parts are written out precisely, and my part is more like cadenzas. So, and that works pretty well. So the piece is very highly structured, and it sounds almost identical every time I play it, even though my part is not written out note for note. That's a very long-winded answer, but the key to that answer is the word mapping, of course.
Okay.
Yeah.
No, that totally makes sense.
Yeah.
No, it's interesting. And thank you for bringing up all these institutions. I think it's great for students. I mean, I was fortunate enough to study in a big part of them, and except for the West Coast that I'm not super knowledgeable about, but I did study at IRCAM, NYU,
Yeah.
McGill and Band Center and all of these places. So
Right.
yeah, so for all my students, you know, it's great that we get a chance to be in touch with all this research at the UFL, and some of you have already done some related topics, right? So it's really good, and I'm hoping that we can have you on campus at some point with your equipment and
Sure.
there's also discussion. I don't know if Kirk is still around, but yeah, it looks like Kirk is still around. But we have discussions about doing something with UVic next year, and the students here. So yeah, we could maybe organize something at UVic instead of just bringing you. But both would be great.
Yeah, absolutely. Any aspect of collaboration, we're open to that. Thank you.
Yeah, no, us too. And I mean, we in Western Canada, it's a very large place in the world, but it's also not so big in terms of number of people in the field, right? So if we put our strengths together, that would be great.
Oh yeah, I wanted to mention one thing for your students. One thing that's surprising that most people don't know, but we recently brought, for example, Sean Casella, who's the guy who's behind Valhalla DSP, you know, those wonderful reverb plugins. And he came to Victoria for a few days, and he was amazed at how much music technology, how many companies there are that do music technology in Victoria. So that's something your students probably don't know, that a few miles west of you, there's a town full of little companies doing computer music, at least 10, I think. Kirk, how many companies do you think there are in Victoria doing music technology now?
We've got a good 8.
Okay.
It could be more, yeah.
Yeah. So I mean, for example, there was a new company that I just discovered when Sean was in town. Somebody came up to me. I forgot his name. I can look it up. But anyway, he was another company. So maybe close to 10 at this point. But for a little town like Victoria, that's pretty amazing. Sean was astonished. So
just a quick question, if I could, if we got time. Thanks, Andy and Robert. Andy, back right to your first slide, and so Ahmadine's point of also raising the institutional connections. There's 2 characters or 2 people in that picture that I don't know, and their names just went past. So maybe for the students, that would also be useful to highlight who those 2 individuals are.
Going back the slow way. Sure, I could jump back, but anyway, this is review, backwards review. Close. Okay, so Roger Lynn of Lindrum, Dave Smith of Sequential Circuits. Let's see, she is related somehow.
It was Lydia, yeah.
Lydia is related to Theremin. I don't know how. I'd have to look her up. She traveled with Theremin. One thing that Vladimir was somehow a colleague of Theremin. I actually don't remember. And one thing I apologize profusely for, that's very obvious and sexist, is that there's only one person not labeled here, and that one person is female. And I'm really embarrassed by that. She is, you know, Don Buchla's partner, or was at the time, and I don't know her name, and I feel terrible because it's glaringly obvious that this picture is all men except for one woman who doesn't have a name, which is ridiculous. I'm sorry about that. But yeah, this is a picture of tremendous intellectual and creative power. Totally astonishing.
For sure, and if I may just add something for students, we have the documentary, I think it's Into the Wires, if I'm not wrong, the documentary about electronic music, especially in the States, between the East Coast and the West Coast, where a lot of those people are like interviewed and are talking. So it is online. I mean, you can access it from the UFL library easily. So if you need information, I will try to send you an email about that or put a link on Moodle. It's also a good way to spend time.
Definitely. Yeah, they're all amazing. Max is gone, Theremin is gone, Moog is gone, Wessel is gone, Buchla is gone. So they're, you know, that's sad, but in any case, the rest of these people are still with us.
Yeah, and I often hear students telling me, like, you know, since electronic music started, and I say, when that was, I think the end of the 90s. I'm like, well,
yeah,
already. So yeah, that would be a good thing. But yeah, thank you very much.